Hello everyone, my name is Mateusz Pusz. I work at EPAM Systems. I am a member of ICC+ committee, a C++ trainer, and a consultant. Today we'll talk about concepts and ranges. We'll see how concepts are specified, and we'll learn how to use them based on the examples from the standard at ranges library. But first, please note that this is a brand new cutting-edge material. Some of the things described here are still work in progress. Even while preparing those slides last week, I found a few minor issues in the proposals that were already accepted by the committee, and we'll have to fix them. Most of the material presented here was voted and accepted on the last C++ committee meeting in San Diego, less than a week ago. We basically voted on last Saturday. It was a very productive meeting, much more productive than I thought. So thanks to that, we have a lot of material to cover, much more than I thought. So maybe it will happen that we'll not have time for questions at the end, for which I'm really sorry, but I'm here for the evening and tomorrow, so we can discuss stuff afterwards. So it will be a fast and rough ride today. We are short on time, buckle up, and let's start. Today we'll talk about concepts, how they are specified. We'll see some examples from the standard library. We'll talk about iterators, sentinels, ranges, views and range adapter objects, and algorithms. Let's start with concepts. How do you feel about this interface? Does it spell anything about the requirements provided for this function? What does it do? What it takes? What it does? Nothing. But is that much better? This one is strongly typed. It's a C++, yes? But if you think about this, how is better than the one above? It will fail in compile time. Great, yes? We'll have 10 pages of error log to analyze. But still, it's not much better in my opinion. And this one is really similar. Generic lambda from C++ 14, yes? So I claim that unconstrained template parameters are void star of our C++. So why concepts? We have such an unconstrained function template foo. We create a simple structure A that stores the data, and we pass that A to our function foo. We are trying to compile this, and we have an error. As you can see here, we have some stack of function calls, starting from our function foo, that we have some foo impl and foo impl part 1, and somewhere there, begin end doesn't compile. What does it mean? Does it mean that the implementation is wrong and has to be fixed? Should we file a bug? Or we just provided a bad template argument to the function? And for a moment, let's try to be adventurous, and let's try to provide a container for this one, because information about begin and end probably suggests we need a container. So we're passing a list. With list, we have even longer compilation error, with a longer stack trace of function calls, and the compiler complains about some function call lg after 2 underscores, and underscore underscore last minus underscore underscore first times 2. Something is not valid here. So let's try different compiler, vector. We are told to use vectors everywhere. We have even longer compiler here, yes? Issue. Oh, sorry for that. Wrong button. 102 lines more, yes? And even longer stack trace. This is the biggest problem we have right now with unconstrained templates. Yes, we get a lot of warnings and errors in the compiler during compilation process, and those errors are deeply nested in the implementation, in the guts of our functions. And sometimes we know that it's our fault, but in many cases we don't know it. We don't know what's the problem. We don't know if it's a problem with implementation. Should we file a bug to the vendors providing this library? Or is it the fault because we provided something wrong to it? So let's try to fix it. What can we do right now? We can create some type trait, is sortable v, and do a static assert as first line in our implementation function foo. This still doesn't change and make our signature better to analyze, but actually the error is much better, yes? We are not having error somewhere nested in the foo function call stack trace, but we have said that we cannot call foo because our type is not sortable. To go a bit closer to the concepts right now, and to have something in the signature of our function, we can create such a helper called requires that is alias over enable if of bools, and we can state our template as here, that it requires is sortable of v equals true. With that, we have, once again, pretty nice compiler error saying that there is no matching function to call foo of stud vector A because it requires is sortable of v of t. That is false. So what are concepts? In fact, concepts are really easily to move from that syntax to concept sequence because this is everything you have to do. So right now, even without C++20, we can prepare for concepts with such syntax I've shown you on previous slides. With this, we specify the constraints for our function template foo. It's even better if we provide a concept name. That's already provided in ranges library. Looking again into the error, we say that this time we cannot call function foo, not that we cannot find it, like in the previous case, because constraints are not satisfied, our sortable is not satisfied, and there is some indirect three-quick order concept inside that it's not satisfied. So this is how concepts help us provide information in the signature of the function template about the requirements of the types that can be passed to them. What are concepts? Class template, function templates, non-template functions may be associated with a constraint. Constraints specify the requirements on the template arguments, which can be used then to select proper overload during overload resolution or template specialization. Named set of such requirements are called concepts. Concept is a predicate that is convertible to bool, evaluated at a compile time, and is a part of the interface of a template, which is important part here. Concepts are not new. Concepts were standardized as technical specification in 2015, so 3 years ago. For many years, we didn't have any consensus in the committee in how to merge them to the IS. We reached the consensus a year ago in Toronto by postponing some of the features, namely introducer syntax and terse natural syntax. I will show you what it means on the next slide. With adding some additional small changes, P0734 was merged with the standard a year ago. So this is what was accepted from ranges from concepts TS. This is concept definition. We put concept here. We no longer provide bool, and we provide the name of the concept. Then we can provide full or original template notation. Then we provide typical template parameters here, and in the next line we provide a requires clause, saying which concept we want to support for our T. There is also shorthand notation that we can replace type name with the concept name. What was not accepted and merged to the IS is this syntax, terse natural syntax that just use a sortable as a name of a type in a function call. The biggest problem with that is that we don't know if it's a function template or a function because we don't know if sortable is a type or a concept name. Also, this one introduces some additional types to our template. This syntax also was not accepted and merged. In San Diego, a week ago, we updated the shorthand notation. These are the function templates for type parameter and non-type type parameter. These are unconstrained here, yes? To constrain those, we provide the name of the concept instead of type name for type parameters, but in order to constrain the non-type parameters, we don't replace auto with concept, but we put concept as a prefix to auto on the left side. Thanks to that, we always know if you are dealing with type parameter or non-type parameter. Template parameters are not supported in this short form, and concepts are restricted to only have type parameters and type parameters packed as their first parameter in a template. non-type and template concepts are not supported in the short form. We have to use the full form for this with requires clause. Full notation for a concept that has variadic list of parameters may look like this one, that we have a list of t's, and we require that each t is meeting a concept t. Shortcut notation can look like this one for this case, and terse notation that was introduced in San Diego looks like this one. We have basically auto, variadic auto of t's, and we constrain that auto with concept. As you are probably already aware, we just introduced generic functions. So right now, we are able to specify generic functions. This is one more example for the concept that has more than one argument. In such a case, this argument is passed here. Talking about the generic functions. Right now, our functions are really similar to the lambdas that we received with C++14. Yes? When we see auto in a function arguments list, it means that it's a template. We can constrain those autos with concept name on the left side of auto keyword. As I said, auto means a function template. We can constrain nearly every usage of auto in our code. So we can constrain return type, we can constrain variable type, we can constrain non-type template parameter, which you already know. We can constrain new expression. Also, we can constrain our conversion operator in a class. Additionally, we can constrain declared type autos. The only usage of auto that cannot be constrained right now is the usage of structure bindings, for which we don't know right now how to do it properly, so it's not supported. Requires provided in a template signature is called requires clause. It can be provided right after template parameters or after the signature of the function. It has to have following forms. It either has to be a primary expression, so it has to name concept or type trait, or it has to be parentized expression that evaluate the bool. Or it may be a sequence of expressions joined with logical AND or logical OR operations. So we can write something like this for a concept. So this is copyable, that is copy constructable, moveable, assignable. And we use this named concept here. This is the preferred notation. But we can also do it this way. We can provide requires clause and provide all of the list here. We can also provide it at the end of the function, or we can mix those. We can provide copy constructable here, moveable here, assignable here, and all of them are equivalent. Besides having requires clause, we also have requires expression. Requires expression is a pure value expression of type bool that describes the constraints of some template arguments. It's true when the constraint is satisfied, otherwise it's false. Usage of requires like here is not suggested, and it usually is a design error. In such case, it probably means that you wanted to have a concept with some name and use a name here instead of requires. Requires expression takes a simple version. It means that it's an expression here, and that this expression has to be valid. The expression is unevaluated operand, so we don't actually do this operation. We just check it for semantics errors. It may be also a type, so we check if the type is valid, or it can be a compound. Compound means that we provide those braces here around the expression, and we optionally can provide no except or return type requirement. What does it mean? So if we provide no except, it means that our expression provided in the braces cannot throw exception. It has to be a no except function. If we provide a return time requirement with this alternative function syntax, it means that expression E has to have exact return type of type provided here. This meaning was changed in San Diego a week ago, because earlier it meant that it has to be convertible and not exactly the same type. And it's basically equivalent to such declaration. Also, we can have nested require expressions inside here. It means that we can additionally constrain the parameters of this required expression. So let's see some examples of concepts from the standard library. If not noted otherwise, all of those things, utilities, will exist in standard namespace. So this is the list of core language concepts. We have same. It is really simple. It just uses type trait. We have derived from. Derived from uses type trait and is convertible. So you can see it's not exactly the same as is base of, because it demands our class to be publicly inherited from the base. Convertible is another difference from the type trait, because is convertible only demands implicit conversions, while the convertible to concept requires both implicit and explicit conversion. Common reference is a new stuff. It means that both types can have some common reference type that both can be converted to. There's also a bigger concept for a common type. We have integral, sign integral, and unsigned integral. Something is assignable when left-hand side is an L-value reference, when it has a common reference with right-hand side, and our given left-hand side and right-hand side, we can assign right-hand side to LHS, and the result of it will be the same as LHS. Something is swappable. What it means, new customization point ranges swap. Swappable with means that we can swap two types with each other or with it itself. But talking about the new customization points, why we need them? Let's assume that we have a wrapper that just stores some data, and we want to provide swap for every T that this wrapper holds. How are we doing this? Let's assume that you have some structure X that's empty for this case, and it has provided our own custom swap function. To swap stud string, our class X, and integers, what have we provide here? If we provide stud swap here, then first and the third case will be okay, yes? But this one will not work. This one will swap, but will not use our swap function, but will use standard one. So it will compile fine, but will not work as expected. If you provide only swap here, we'll use argument-dependent name lookup to find those namespaces for X and S, but integers will not work. So probably all of you know that in order to make it work, we have to provide using directive here that will just add stud swap to our overall resolution, and in this case, all of three cases will work. This is well-known pattern. However, the same pattern applies to algorithms, and in case of algorithms, we nearly never use this for calling algorithms. What I mean by this? Let's assume that in some corporation, we have some strange container that have some strange interface, and even if we provide non-member functions that will comply with standard library interfaces, we have to provide those using stud begin, using stud end, in order to this algorithm work with, for example, our strange container and constant C-style array of characters. And this is not often used by us. So, as I said, those new customization points are customization point objects. They are different. So let's see how we construct such objects and how they work under the hood. So let's assume that we want to create a customization point object for our operation named myOp. Is it an object? Then we have to create this object. It will be of type fn in some namespace, myOp here. This functor has to provide the default implementation with maybe some constraints. And also right now we have to provide ADL version of our customization point. In order to do this, we have to find out if this ADL version is provided by the user. So we create some type trait called has customization. Default is false. But if the user will provide such an operation that is valid, it will be true. having this trait, we can provide another overload that has additional constraints on this trait that will call our myOp function using ADL. So everything is nearly fine here. The last thing we have to do is to block non-ADL lookup, so we'll not go out of the scope of this namespace higher in namespaces to look for overloads. So we provide anything here that has the same name as our customization point in order to block further lookup in higher namespaces, including the global one. So this is how all the customization point objects in ranges library are created. This is something new, so that's why I wanted to show you how it's done under the hood. So coming back to the ranges swap. Ranges swap does swap E1, E2 if it's specified by the user. It finds it with ADL. And additionally, it has so-called poison pill that adds additional to overload resolution such signatures. So the default implementation from namespace tut will not be found. If we are working with arrays, that just swap ranges on those two types will be called. Otherwise, if E1 and E2 models move constructable and assignable, so basically swappable, then we'll exchange the denoted values. So this is an example how we are using those customization points. We have some structure A that stores M. We have a proxy that stores a pointer to A. If you want to swap those two types with each other, we can do it by providing our own customization point. And as you can see, we are using here fully qualified swap. That just moves M from one to each other, swaps the M. In order to satisfy symmetry requirement, we have to provide other overload with reversed parameters and just call the same function. If you want to write our algorithm right now, that will use swap, we are doing value swap that takes two template parameters, and we call tut ranges swap, again fully qualified, and provide this T and U, and everything will work fine. So with ranges, we don't have to do any using directives, and we call our customization points with fully qualified name. Coming back to the concept, something is destructible if it's no-throw destructible. It's constructable when it's destructible and constructable. It's default constructable when it's constructable without any additional arguments. Move constructable and copy constructable are self-explanatory. We have concepts for Boolean operations, for comparisons. Boolean is satisfied when the type is convertible to bool and provides Boolean-like operations, so negation, logical and or, and equality and non-equality operations that are convertible. Their results is convertible to bool. Equality comparable requires us to provide equality and non-equality operations that the result satisfies Boolean concept, and strict totally ordered has to be equality and provides also less, greater, less equal, and greater equal operations. We have also concepts for objects. Object is movable if T is an object, if it's move constructable, if it's assignable, and swappable. It's copyable if it's copy constructable, movable, and assignable. It's semi-regular when it's copyable and default constructable. And as we've heard yesterday from Victor, regular types are really important. We have a concept for them. Its regular type is a semi-regular type and equality comparable type, so we have equal and not equal provided for them. Beware, there are ogres here. If you have a class A that has a constructor, destructor, it's put as an aggregate to class B that has default constructor, it turns out that our class B is not default constructable. Why? Because we provided a really strange destructor. We provide a destructor that can throw. If you have such a destructor in your classes, it will not make your class meeting the default constructable concept, so it will also be not regular, So it will not work with most of the ranges facilities provided in the standard. Another example here is struct C that has a constructor, copy constructor, assignment operator, and destructor. It also provides equality and non-equality operations to satisfy regular concept, but it doesn't satisfy it. Why? Because we spelled assignment operator in a strange way. It returns void. I know that some guys do it. They claim that it's safer because we cannot chain assignment operators thanks to that, but then again makes our class non-regular. So beware of such constructs. They will not work fine with ranges library. The last concepts that we'll see here from the standard library are concepts for callables. But first, we have to know what does it mean to be equality-preserving expression. Such an expression is an expression that, given equal inputs, gives this equal outputs. And not all inputs have to be valid. For example, if you create the division operation and we provide second argument as 0, it's not well defined, but it doesn't care here. It doesn't have any problem. Equality-preserving expressions are further required to be stable. So it means that if you provide the same inputs many times, you will have the same outputs every time. We are talking about this because expressions declared in requires expression has to be required to be equality-preserving. Of course, C++ wouldn't be a C++ if for every rule there was no exceptions. So we have also exceptions here, except noted otherwise. So first case, when it's noted otherwise, is invocable. Invocable is a functor that can be called with arguments, and this invoke function is not required to be equality preserving. We have regular invocable concept that means that this time invocable is equality preserving. The distinction between them is purely semantic, and you have to provide correct information to your classes because ranges will not be able to detect them based on your interfaces. Predicate is a regular invocable that is converted, that the result is a Boolean concept. Relation is the predicate between T and U classes. Strict order is a relation that supports strict ordering between its arguments. And with that, we are ready to go into new stuff from ranges library. If not noted otherwise, the following utilities exist in stud ranges namespace. To talk about the iterators, we have to know what does it mean to increment iterator and what does it mean to have a distance between those two objects. So there is a new type trait called incrementable traits. Incrementable traits is specialized for pointers. In such case, the difference is pointer diff. We just remove const and do the same here. And if difference type is provided in a type, then we are using the difference type in our traits. If this difference type is not provided, but the subtraction of A and B gives us integral type, then we are using this type converted to a signed version as a difference type. Our iter difference alias will be either iterator traits of I difference type if it's valid, specialized. Otherwise, we'll use this incrementable traits above to provide difference type. So users may specialize incrementable traits on their defined types to provide difference type for their iterators. The same is true for the next one. Those are readable traits. So if we want to read something from an iterator, we have to know what value is being stored there. So if you have a pointer, we just say that our value is t. If we have an array, we remove extents. If we have value type or element type inside our type t, we are using those for our value of the iterator. And again, we have an alias here called iterValueT that takes iterator traits value type if specified. Otherwise, we have value type. Those are customization points that you should use and create for your types if needed. Also, as you know, we have iterator threads. Iterator threads were updated to provide support for concepts, as the concepts are not compatible in some points with standard library algorithms. And so basically, ranges are not compatible with algorithms. We have to provide some other tag for iterators. So it may sometimes happen that iterator concept will be different than the one provided for old STL algorithms. With providing iterator concept tag, it means that you are subscribing to ranges. Otherwise, your iterator will not work with ranges. Another customization point that you have to provide is what does it mean to move a value from your iterator. So if you provide such a customization point, it will be used. Otherwise, if the referencing of E is well-formed and is an L value, we use std_move of the referencing. Otherwise, we just use the referencing of this iterator. So for example, if you want to customize it, you write your own iterator. A common iterator is some wrapper around another iterators. So in order to make it work with iter_move, we do iter_move on the nested iterator. This is how you specialize those customization points for your iterator types. Some iterators has to be readable, so you have to provide a concept for it. Something is readable if it has value type, reference type, and R-value reference type, and they have common reference. Writable is something that can be assigned to our dereferenced iterator type. Weakly incrementable is semi-regular and provides pre- and post-increment operations. Weakly incrementable types means that if you have A and B of the same value, that are equals, it doesn't mean that if you increment both of them, you will get the same thing. So this is true, for example, for input iterators. Algorithms on weakly incrementable types should be only single-pass algorithms. Incrementable, on the other way, means that you have to provide here the regular type, and it's required to be equality preserving. So you can use it with multi-pass algorithms. So iterator, finally, we have a concept for iterator. It requires that iterator can be dereferenced, and it's weakly incrementable. So every iterator satisfies this concept. Sentinel is, as you can see, provided for two types. So something is a Sentinel, which for iterator provided for the Sentinel, you are able to compare this Sentinel and iterator type. SizedSentinel is something that can provide operator less or minus here, and this operation is being done in a compile time, constant time, sorry. So if you have an iterators that basically has this operation less but doesn't provide it in a constant time, you can disable it with using of this disabled SizedSentinel customization point. For example, you can do it for reverse iterators. InputIterator is an iterator that is readable, and it's derived from the InputIterator tag. Difference from the C++17 InputIterator is that this concept doesn't have to be equality comparable, because we are not comparing InputIterator with another InputIterator like it was the case in C++17 and earlier. We are comparing InputIterator with a Sentinel type. So we don't have to make InputIterator comparable. OutputIterator is an iterator that is writable and should be used only in single-pass algorithms. Forward iterator is self-explanatory, and similar is for bidirectional stuff that provides us subtraction, not only a plus operation, and random access that provides us more operations to our iterator. We have also the Contiguous Iterator that makes sure that we work on the contiguous memory. Sorry for going so fast, but we don't have much time today. Iterators and Sentinels, we also have new classes, not only concepts. First of those classes is a really simple class called default Sentinel. It's an empty class, and it's used to denote the end of the range. It is intended to be used with other iterators that know they are bound. For example, Contiguous. Talking about the Contiguous, it's a new type provided in the library. It's an adaptor over another iterator that basically tracks of its distance from its starting position. As I already told, it can be used with default Sentinel in such a way. Let's assume that we have list, we have vector, and we can provide counter iterator of list begin, and it will count only 10 times. And we don't have to provide the end iterator of list because it will not be cheap. We provide a default Sentinel here. So this is basically an equivalent of copy n operation from the previous library. Also, we have an Unreachable Sentinel class. Unreachable is used to denote the upper bound, and it's strange type because for every comparison it returns false. It means that you can never reach the Unreachable Sentinel. It can be used in such a case that, for example, you have some characters, string of characters here, and you're looking for the new line character in the string. If you are sure that it exists there, you can provide the Unreachable Sentinel here, and it will just iterate over P until it finds this character. It theoretically is faster than the typical solution because our if branch in our if in the for loop is not a branched expression because it's always false. Another class here is a move Sentinel that provides us the move operation, and together with move iterator can provide us move semantics, for example, for copy if algorithm. So if we have copy if, we provide move iterator and move Sentinel, we will be moving instead of copying that stuff to the output. Common iterator and the family of common things we'll talk about today means that these are adapters that are provided different types as an input, iterator and Sentinel as a separate types, but they will provide iterator and Sentinel of the same type. They are mainly meant to be used with legacy stuff that has this requirements of providing the same type as a begin end, like all of the algorithms in our current implementation that we have. So for those, having for our list, we can create a common iterator type for counter iterator on the list, iterator, and default Sentinel. So having those two different types, we can have one type produced by this common iterator. So we create here our functor, and we provide and construct this common type from counter iterator and from default Sentinel, and it will work fine for begin and end. Okay, let's move to ranges. A range is an iterator and a Sentinel that designate the beginning and end of the computation. A counted range is an iterator and a count that designate the beginning and the number of elements to which the computation is to be applied. Iterators and Sentinels that denote a range are comparable. We have advanced for those. We have distance. We have next, previous, and we have new customization point objects for begin, end, and all of the operations we know. Why new? Because, again, things we have were a bit broken, so we had to provide better alternatives. How they work? Basically, ranges begin will return us the beginning of array if we are dealing with L value of array type. If it has member function begin, it will use member function begin if this function returns us something that models iterator concept. Otherwise, we'll be looking for non-member begin function, And it also has to satisfy the iterator concept for the return type. It is being done with the interesting overload resolution here. We basically remove here the support for temporaries. User can opt in for supporting temporaries or values for types that are fine with that. So for example, string view or other views are fine because when they expire, iterators provided by them are still valid. Range is something that has begin and end. Size range is a range that has a size that is calculated in constant time. If your container doesn't support that, you can use disable size range to remove that. Yes? So if you have a container that calculates size in a linear time, for example, then you shouldn't. You should provide information that it's not a size range. We have also output range, input range, forward range, bidirectional range, random range, and contiguous range that is specified according to their iterators. And again, we have something called common range that has the same types for Iterator and the Sentinel. OK, so let's go to the more exciting stuff. Let's see how views are created. View is a range, it's semi-regular, and it has to support something called enable view. We'll be talking about this on the next slide. The view concept specifies requirements on a range type with constant time copy and assign operation. The cost of this operation is not proportional to the number of the elements in the view. And since the difference between range and view is purely semantic, we cannot detect this by ranges, so we are using that enable view trait to know if something is a view or not. So this is, again, a customization point that you should provide for your types. It is true by default if your type is derived from viewBase, with viewBase being an empty class. It is false if basically const iterator and iterator are of the same type. If they're on the same type, it means that you have view semantics, like, for example, string view. If they're on different types, it means that you have ownership semantics, and this is probably a container, so it's not a view. It's true otherwise. There are, however, some containers in the library that doesn't satisfy this. Namely, those are initializer list, set, multiset, unordered set, and unordered multiset, for which the iterator and const iterator are of the same type. So we have disabled this. And if you have similar containers in your libraries, you should do the same. This is only one exposition, only concept I would like to show you because it's a really interesting one. It's the range for which the validity of iterators is not tied to the lifetime of an object. It means that even if the type provided as an R value of such range will expire, still iterators and things that they point to are valid that didn't expire. This is true for things like span, like string view, like subrange. Viewable range is a range that can be converted to a view. View has following interface. It derives from viewBase. That was empty, as you remember. And it has empty and operator bool. It has data and size. It has front and back. And has indexing operator. Subrange is first of the views we see today. It's just a part, contiguous part of the views of some bigger view. And again, common view is something that has the same type for Sentinel and Iterator. So for example, once again, if we have some legacy algorithm with the same types provided as begin and end, we can create a common view of our range. The range can have different Iterator and Sentinel. We do not know here, but in any case, we want to be safe with this algorithm. And we can then just do command begin and command end, and it will return us the same type, even though the initial range had different types in they are in the type for Iterator and Sentinel. All view is a view that returns everything from the range. Empty view is an empty view. Single view is a view that has only one element. Reverse view is a bidirectional view that produces another view that has the same elements but in reverse order. So when we have a vector of integers and we have a reversed view, we can print all of them and we'll find out that they are printed in reverse order. Transform view is a view that applies the transformation provided by our functor. So we have here a transform view that squares provided value. So the output of printing such a view will be 0, 1, 4, 9, 16. IOTA view generates a sequence of elements starting from provided value. Filter view filters elements from the range with provided predicate. Take view takes at most n elements from another view. So it will take only 5 of first elements here. Take while view will take first elements that match predicate. For example, here we'll take all elements that which square is less than 20. Drop view is totally reversing of the previous page. So it takes all but first n elements and drop while all but first elements that satisfy the predicate. Join view is a view that joins a collection of views into one view that can be iterated by character, for example, and printed. If you have join, we have to have split, of course. So we are able to split stuff based on provided delimiter. So a result of it will be a collection of views that can be iterated here. Views work really nicely with range adapter objects. Range adapter objects is a functor that takes a view as an argument here. And it has two syntaxes. Either we can create adapter providing range here to the call operator or constructor. And then we can also provide range and operator bool overloaded here, or pipe, like you noted from Unix systems, and then provide the adapter. If our functor takes more than one argument, we can provide those here or here, and there's additional syntax where we can provide arguments here and range as the last braces. So how does it work? Those things are declared in ranges view namespace. They have the pipelines to evaluate lazily over the range. And they are using for this bitwise operator that is overloaded. So when we have a vector of integers, and we have functor that checks if something is even, and we have another functor that squares provided value, then we can create that our loop goes on those integers. We filter only even elements, and then we transform them to calculate their square. It will print 0 for 16. So this is how range adapter objects work. To better understand the difference between views and range adapter objects, let's see how they are implemented once again. Views are something that is inherited from view interface, provide basically begin end and other stuff connected to view interface. And range adapter objects are objects, yes? So these are objects of some functor, and this functor is implemented here. It has some pipeable interface that it can provide those pipe operations, and it basically, in call operator, it creates our view that we are working with. The last thing I wanted to show you today are algorithms. We have overloads of nearly over all of the algorithms from the standard library for ranges. we'll look only on a few of them, but in order to look on them, we have to know a few new stuff. We have our own function objects in ranges. These are not templates, as you can see, because we are using only this so-called diamond operator syntax. So things that are, those are transparent functors, and they provide call operators that are templates. Similar definition is provided for not equal to. Less is also transparent, but requires strict totally ordered with. We have here equality comparable with, yes, for equality comparisons. Here we have strict totally ordered, and the same is provided for greater, greater equal, and less equal. Another new thing here are projections. Projection is a transformation that an algorithm applies before inspecting the values of elements. For example, if you want to sort pairs by first argument, we run fully qualified stud ranges sort on our pairs. We provide stud ranges less as comparison. And then we want to say what we want to compare. So we want to compare only first elements of those pairs. Of course, the result will be full pairs being sorted, but only for the sorting reasons we use the first element of pair. Lookup of the algorithms is different than for namespace stud. Basically, they are not found by argument-dependent name lookup. We have to fully qualify their names. If we provide using namespace stud ranges in our function, they still inhibit argument-dependent name lookup. So what that means, if you have stud vector here, and you will call find without any qualification for begin vector and vector, we don't call the stud find algorithm, the old one, but we'll call the stud ranges algorithm. So the stud find will not be found in this case. Overloads of algorithm that takes range as an argument behave if they are implemented just calling begin end on the range and calling the version of algorithms that take iterator and sentinel parse. So this is our own old find if with two input iterators and predicate. This is our new find if in ranges namespace. It takes iterator, sentinel, projection, and unary predicate. We have also version for range. As I said, it's exactly the same as we would just call range begin, range end, and call this one. Another important, really important stuff here is this safe iterator returned from the ranged version of the algorithm. Safe iterator is something that is iterator if our range is a forwarding range that we mentioned, or dangling type otherwise. Dangling is a special structure in stud namespace that is just possible to create from everything and doesn't have any semantics. So why is that? Let's see an example. When we have a function that returns vector int by value. We want to find integer 42 in our vector. Yes, we pass here the result of our function f. It's a temporary, it's an R value, and we get an iterator here. If we will try to dereference the iterator later on in our code, our vector is already out of the scope, yes? It's already destroyed. So it will be unsafe. That's why ranges automatically return you the dangling type. If you try to dereference it or do any iterator connected operation with it, the code will not compile because to say that you cannot do an operation on a dangling type. However, if you will create an L value of vec and provide this L value to our ranges find, it will work just fine. You will get an iterator as a result. If you are passing a forwarding range even as an R value, as a temporary here, so for example, subrange or string view or another range or another view, it's fine, because even if this subrange is destroyed or a string view is destroyed, still this iterator can be dereferenced fine. So, to summarize, takeaways for today. Constrain your template parameters with concepts. You can start thinking about this already with the syntaxes I provided to you. Start writing type traits to find the constraints you have. Maybe do static asserts, or even better, use this requires tool that I provided. It's much easier than even with some automated script, we'll be able to convert those to later on to C++20 concepts. Learn and use what you have already in the library, yes? Do not reinvent the wheel. And besides, just by going through all those types, you learn how to use concepts. As you can see, probably you're already tired with all of this. You didn't expect that you will see so many concepts today. Limit requires usage. Do it only if really necessary. Otherwise, create a named concept and use the named concept for those. If needed, provide customization points for your custom types in order to make them work with facilities in a ranges library. Prefer usage of the algorithms from stud ranges rather than those from namespace stud, because those are safer. Work on ranges and provide you those dangling iterators. They have a lot of benefits there. OK, photos done. Last slide for today. There are two implementations. One is implementation from Eric Niebler in Range v3 library. This is how it started. It is compatible with C++11, work with Clang and GCC. It's not exactly the same as in standard, but it's fully functional and backward compatible. Another library from Casey Carter is the one that works only with GCC with F concepts, so the concepts TS. It's nearly exactly the same as the standard. Probably Casey will catch up with the things we standardized a week ago there, because he was spending most time lately on doing papers rather than coding. So probably have to catch up a bit. But it's the equivalent of what we have in a standard. So you can play with it and try to work with those libraries right now. It seems that we have like 2 minutes left, so maybe we have time for one question.
Really quick questions. Are concepts namespaced?
Namespaced?
Yeah, if I have like concept
yes.
iterator,
yes,
uppercase I,
yes.
and I have a struct iterator,
all
will those clash?
Yeah, all concepts are in namespaced. They are written from the big letter, so they will not clash with anything in the standard library. All concepts regarding the core stuff that we've seen, as I said, are provided in the namespace stud library, or concepts provided for working with iterators, sentinels, and ranges, and views are provided in stud ranges library.
Awesome, thank you.
Sure.
Just a quick question. Is there any reason not to use ranges?
For now, I don't know that use case. Probably for now you can't just use ranges because it's not there. No, I mean, but if it will be there, yeah. I think that's really awesome stuff to try and work with.
OK, thanks.
Thank you. If there are no further questions, or you have other questions later on, then you can catch me up in the evening or tomorrow.
I have one more.
OK.
Is there a reason for separating the projection and the predicate in the find-if algorithms?
Projection and predicate. Yeah, I think so, because in that case, you just, for example, can use stdless for everything. You don't have to write your own predicate to extract stuff. So you can distribute things to compare and things to filter stuff from your structures. In case you would like to, for example, sort your custom type in different stuff, in different orders, like in less, greater, less than, and have different containers, you would have to type it many times and do extraction and comparison at the same time.
OK, so it's composability.
Yeah.
OK. Thanks.
OK, we are out of time. Thank you very much. Have a good evening.